Astronomers expected a bright and dramatic sight when their telescopes finally regained view of 3I Atlas on November 5, 2025. They believed the comet would show a long glowing tail because it had just passed its closest point to the Sun, a stage when every known comet becomes more active and releases dust and gas into space. Instead, they saw something that froze the entire control room. There was no tail, no spreading coma, and no cloud of dust. All the instruments detected were a single tight point of light, a result that broke every basic rule of how a comet should behave after perihelion. This strange silence forced scientists to confront a disturbing possibility. Something had happened during the 3 weeks when the comet was hidden behind the Sun, out of sight and beyond the reach of every observing tool on Earth. What exactly could shut down a comet at the very moment it should have been at its brightest? The setup begins with the speed of 3I Atlas, because it entered the inner solar system, racing between Earth and Jupiter at about 129,742 miles per hour, making it the fastest interstellar object ever recorded. Before it reached perihelion, astronomers watched it grow more active every week as a dust coma expanded around the nucleus and gas emissions increased in strength. Images also showed a young tail beginning to stretch behind it, and in August, the object even produced an unusual anti-tail that pointed toward the Sun due to slow-moving ice grains. By early October, the color of the comet shifted toward an impossibly blue tone, a change that confused observers who knew normal comets always appear redder than sunlight. All activity seemed ready to peak, yet the comet reached perihelion on October 29th while completely hidden behind the Sun, forcing every Earth-based telescope to lose sight for 3 weeks. When it returned on November 5th, the transformation was total because the previously active object now appeared as a silent point of light with no visible signs of energy. Current brightness measurements show a steady fade from magnitude 16 to magnitude 20 by February 2026, and the object will become untrackable by June. The real question now is how much can scientists uncover during the final 4 months before this ancient visitor disappears forever? The central idea of this chapter begins with the strange silence of 3I Atlas, because a comet should always grow more active after it passes perihelion. This behavior is one of the simplest rules of thermal physics, and it has been confirmed through many decades of observations in the solar system. When a comet moves close to the Sun, intense heat strikes its surface and begins to travel deeper into the interior. This heat does not disappear once the comet moves away, because thermal energy continues sinking downward through layers of dust, rock, and frozen material. Scientists call this process thermal conduction, and it ensures that deeper ice keeps sublimating long after the comet leaves the hottest part of its orbit. This usually creates the brightest stage of a comet's life, since the inside remains warm even while the surface cools. For this reason, astronomers expected the 3I Atlas to become extremely active when it returned from behind the Sun. The final images captured before the blackout supported this expectation, because its brightness was rising steadily. The dust coma around the nucleus had been expanding, which suggested that deeper layers of material were breaking apart. Gas emissions were also increasing, and these changes usually mean the inner regions have reached temperatures high enough to release more volatile compounds. A developing tail had already begun to stretch outward, and its early shape suggested it would become much larger after perihelion. All available data showed that the comet was preparing for its most intense phase. This is why the silence that followed shocked the entire scientific community. When the blackout began on October 15th, every Earth-based telescope lost sight of the comet for 3 weeks as it slipped behind the Sun. During those weeks, researchers reviewed the last measurements again and again, trying to predict how dramatic the post-perihelion outburst would be. Many expected a bright tail stretching millions of miles, along with strong dust and gas activity. But on November 5th, the object returned as nothing more than a compact point of light. There were no jets, no dust, and no signs of sublimation anywhere near the nucleus. Even the weak activity recorded in early observations had disappeared completely, leaving an object that looked more like a quiet asteroid than a comet still carrying stored heat. This transformation made the mystery even deeper, because no known model of comet behavior can explain a complete shutdown at that stage. A comet cannot cool instantly after receiving extreme heat, and the inner layers should have still been warming during that exact period. Researchers compared this to a pot of water reaching boiling temperature and then suddenly turning into ice the moment the stove is turned off. Such a reaction has no physical support, especially for an object filled with frozen material. This unusual behavior forced astronomers to consider explanations that went far beyond normal expectations. One idea proposed that the comet might have broken apart during the blackout, leaving pieces too small to show strong activity. Another theory suggested that the surface could have become sealed under a thick crust created by intense heating, trapping all remaining gases inside. A third possibility argued that the comet had exhausted all of its volatile ice and had nothing left to release. Each explanation describes a different kind of catastrophic event, and each one changes how scientists understand the nature of interstellar objects. The challenge now is deciding which scenario fits the evidence most accurately, because each one leaves questions that have not yet been answered. New observations will help researchers narrow the possibilities, but every new detail adds more tension to the mystery that began during the blackout. This leads back to the central question that drives this investigation. Did the comet break apart, seal itself, or lose everything during the one moment when no one on Earth could watch? The second chapter begins with the 3 main explanations scientists are using to understand the sudden silence of 3I Atlas, because the comet's behavior after perihelion created a mystery that normal models could not explain. The first idea focuses on fragmentation, which suggests that the nucleus may have shattered under the intense thermal stress it experienced near the Sun. This event could have happened during the blackout, and the pieces would have been too small to generate a visible tail or a bright coma. Fragmentation is a known process in comet science, and several examples support this possibility. A major case appeared in 2020 when Comet C 2019 OP-Y4 Atlas completely disintegrated into dozens of tiny fragments, leaving only a faint debris cloud behind. Another example comes from the interstellar comet Borisov, which lost about 0.1% of its total mass in a single event during its approach to the Sun. These cases show that thermal stress can break a comet apart without warning, and the same type of structural failure could have happened to 3I Atlas. If the nucleus shattered, then the quiet point of light seen after the blackout would make sense, because each remaining piece would be too small to maintain strong outgassing. Many astronomers believe this explanation is possible, yet they also note that the pre-blackout data did not show a sudden drop in brightness, which usually appears before a comet breaks apart. This detail creates doubt, so the fragmentation theory cannot fully answer the mystery on its own. The second idea is total volatile depletion, which argues that all sublimatable ice inside the comet may have been burned away during the extreme heat of perihelion. Volatile ice includes carbon dioxide, water, and carbon monoxide, and these materials normally drive the outgassing that creates tails and comas. If these ices were completely exhausted, then nothing would remain to produce any kind of visible activity. This theory describes a comet that has turned into an inert object made mostly of rock and dust, unable to release gas even when heated. Some scientists believe this scenario is possible because the comet produced strong activity in the weeks before perihelion, which suggests that the shallow layers of ice may have been consumed quickly. However, depletion raises another problem, because deeper layers usually remain untouched, and thermal conduction should keep them active long after the surface cools. If all volatiles disappeared, the comet must have burned through every reservoir of ice, including the deepest pockets, which seems unlikely when the blackout lasted only 3 weeks. This detail makes the second theory incomplete, and scientists continue to question whether total depletion alone can explain the complete silence of 3I Atlas. The third explanation is mantling, which suggests that radiation-processed organics on the surface melted and fused during perihelion, creating a sealed crust similar to a layer of cosmic asphalt. This crust would trap all the remaining volatiles under a hardened shell, preventing them from escaping into space even if they continued to heat up. Mantling is known to happen in old comets, and some extinct comets inside the solar system show similar sealed surfaces that hide deeper layers of ice. If 3I Atlas created such a crust during perihelion, then the object would appear completely inactive, even though its interior still contains frozen material. The mantling hypothesis explains the sudden shutdown more cleanly than the first two theories, because a sealed crust could form within hours under extreme heating, and the blackout window gave enough time for this process to complete. This idea also fits the fact that the comet did not show a brightness collapse before the blackout, because mantling does not always change the light curve before the transformation occurs. However, mantling still leaves questions, because scientists want direct evidence of cracks or variations on the surface that would confirm the presence of a crust. To address these questions, the Hubble Space Telescope completed a new observation run 3 days before the transcript's timeline, and its results will help confirm or reject major fragmentation in the coming weeks. The outcome of that observation will guide researchers toward the most likely explanation, yet the mystery still depends on details that no one has fully understood. This leads to the central question at the end of this chapter. Which of these explanations matches the impossible silence we are seeing now? The chemistry of 3I Atlas became one of the most shocking parts of this investigation because the measurements collected before perihelion revealed a composition no one had ever recorded in a comet. The data showed that 87% of its gas output came from carbon dioxide, while only 4% came from water vapor. This finding surprised researchers because comets are normally built from water ice mixed with smaller amounts of carbon dioxide and carbon monoxide. The imbalance in Atlas went far beyond a simple difference in proportions and created a ratio that sat 6.1 standard deviations beyond normal comet values. In scientific terms, a result that far outside the expected range means something extraordinary shaped the comet's chemistry. The production rates strengthened the mystery even more because the comet released 129 kilograms of carbon dioxide every second and only 6.6 kilograms of water vapor. These numbers contradicted every formation model used to describe how comets develop in young planetary systems. Standard models predict that 70 to 80% of a comet's volatile content should be water ice, since water condenses easily in cold regions of a forming solar system. Carbon dioxide normally plays a supporting role because it freezes at lower temperatures and exists in smaller amounts. Nothing in those models explains how a comet could end up dominated by carbon dioxide while carrying so little water. This contradiction forced scientists to search for an explanation that did not come from ordinary processes inside a system like ours. The leading idea points toward radiation chemistry, which happens when an object spends billions of years exposed to cosmic rays in deep space. Cosmic rays can break apart chemical bonds, rearrange atoms, and slowly reshape the structure of frozen materials. Over long timescales, these rays could convert carbon monoxide into carbon dioxide much faster than it forms naturally. They could also strip hydrogen from water ice, weakening the water content and leaving behind oxygen-rich residues. If Atlas traveled through interstellar space for billions of years, then its outer layers would have experienced these reactions many times. This means the strange composition scientists observed may not reflect how the comet formed, but how it changed over extremely long periods of radiation exposure. The idea becomes even more interesting when researchers think about the comet's age. Based on its chemistry and trajectory, many scientists believe that Atlas may carry ice older than the Sun. Its material may have formed in the early thick disk of the Milky Way, a region populated by ancient stars that existed 10 to 14 billion years ago. If this timeline is correct, then the comet contains frozen chemicals from a period when the galaxy was still assembling its first structures. Every measurement hints that Atlas is not simply an interstellar object passing through our system, but a survivor from the early universe. The numbers create a sense of awe among researchers because they represent a direct connection to environments that existed long before Earth formed. Studying those materials could help scientists understand conditions that shape the earliest stages of star and planet formation. However, the comet's sudden silence makes the situation more urgent because there may be only a short window left to examine these signatures. If the object never becomes active again, then the chemical data collected before the blackout might be the only record of these ancient processes. This possibility makes the mystery of Atlas even deeper. If its chemistry belongs to the early universe, how much of its structure does too? The strange behavior of 3I Atlas became even more dramatic when astronomers noticed a sudden change in its brightness during the final days before the blackout. The comet began to brighten far faster than normal, and the increase did not match any pattern seen in typical comet activity. As the light grew stronger, observers noticed that the color of the glow shifted toward a deep blue, something no one expected to see. This change immediately raised alarms, because comets are supposed to look redder than the Sun when their dust reflects sunlight. Dust particles always scatter longer wavelengths more efficiently, and this creates the warm red tones usually seen around active comets. Seeing Atlas glow bluer than the Sun broke one of the most basic rules of optics, and the data showed that the shift was not a measurement error. The brightness curve confirmed a real transformation happening around the nucleus, and scientists began searching for a cause. The only explanation that fit the color was emission, meaning that the gas around the comet was producing its own light instead of simply reflecting sunlight. Carbon dioxide can emit blue light under strong solar radiation, and this reaction is known as fluorescence. However, the intensity needed to create such a bright blue glow is far beyond anything ever recorded from a comet. This forced researchers to consider whether Atlas had released a type of gas mixture that reacts unusually under high energy exposure. The blue phase lasted until the object disappeared behind the Sun, and it ended so abruptly that many scientists believe it was connected to whatever happened during the blackout. The blue glow alone was a mystery, but another discovery made the situation much stranger. As researchers studied the pre-blackout spectra, they detected clear signatures of atomic nickel located within 594 kilometers of the nucleus. Nickel is not a rare element in comets, but it is always found together with iron because both elements form through the same nuclear reactions inside dying stars. Seeing nickel without iron breaks one of the simplest chemical laws of the cosmos, and several teams rechecked the data to make sure the readings were accurate. Every analysis confirmed the same result, which meant that the iron expected to accompany the nickel was truly missing. This absence baffled researchers because there is no known way to separate iron from nickel during a comet's formation. The spatial distribution added another clue, because cyanide signals extended outward to 841 kilometers, much farther than the nickel. This suggested that complex molecules containing nickel might have been breaking apart near the nucleus while other fragments drifted outward. Some scientists proposed that the comet could contain exotic organic compounds that incorporate nickel in ways that do not occur naturally in the solar system. Laboratories attempted to create similar compounds under different environmental conditions, yet none of the experiments produced anything close to the spectral patterns recorded from Atlas. This failure made the nickel puzzle even more important because it hinted that Atlas contains chemistry shaped by environments that no longer exist in the galaxy. The combination of blue fluorescence, missing iron, and unstable nickel compounds created a picture of a comet that refuses to follow the rules that shape everything else in the sky. Each anomaly pushes Atlas further away from being a normal interstellar object and closer to being a relic from a time when the galaxy was still forming its earliest structures. If this is true, then its strange glow and unusual chemistry are not accidents but signatures of its origin. This leads to the core question of this chapter. Why is this interstellar object breaking the chemical rules of the cosmos? The motion of 3I Atlas became even more confusing when astronomers noticed that its path through the solar system did not follow the behavior expected from gravity alone. Precise tracking revealed a steady non-gravitational acceleration, which meant that some kind of thrust was pushing the comet faster than the sun's pull could explain. This discovery created a serious puzzle because telescopes saw no outgassing, no dust jets, and no visible signs of activity around the object. In a normal comet, acceleration comes from jets of gas shooting from the surface, acting like thrusters that push the nucleus in the opposite direction. These jets always leave clear signatures, yet Atlas showed none, even when observed with some of the most sensitive instruments on Earth. The absence of visible activity forced researchers to look for explanations that matched the physics but remained hidden from direct observation. One idea suggested that the comet could be releasing hydrogen gas, which is invisible from Earth because the ultraviolet wavelengths needed to detect it are blocked by the atmosphere. Hydrogen outgassing would produce real thrust without creating any structure that telescopes could see, and this made the explanation possible. Another idea pointed toward heat stored deep inside the comet during perihelion, which could still be driving sublimation from sealed pockets beneath the surface. In this case, the gas would escape through cracks too small to create visible jets, but strong enough to influence the motion of the nucleus. A third possibility argued that the thrust pushing Atlas today may have been created before perihelion, and the change in velocity simply continues along the path even though the jets have stopped. This idea suggests that the comet received a strong impulse during the blackout and now carries that momentum into the outer solar system. All three explanations propose hidden forces, and each one tries to match the data without breaking known physical laws. But the comet's path made the mystery deeper because its orbital eccentricity measured 6.14, the most extreme hyperbolic trajectory ever recorded in an interstellar object. Such a high value means Atlas is not gravitationally bound to the Sun in any way, and no encounter within the solar system could have given it this speed. It entered fast and it is leaving even faster, with an acceleration that scientists can measure but cannot directly observe. This strange motion makes the coming months even more important because the final chance to test every theory will happen on March 2026 during the Jupiter flyby. The comet will pass only 0.36 astronomical units from Jupiter, a distance close enough for the planet's tidal forces to stress any sealed crust or weak structure. If Atlas formed a mantle during perihelion, then the gravitational pull from Jupiter might crack the surface and allow trapped gas to escape again. A sudden rise in activity would confirm that the comet sealed itself, matching the mantling explanation. If nothing changes during or after the flyby, then the depletion theory becomes the most likely answer because a comet without volatiles has nothing left to release. However, if the nucleus fractured during the blackout and Atlas is really a cluster of fragments, then Jupiter's gravity will pull the pieces farther apart. In that case, telescopes will see multiple sources instead of one, and fragmentation will be confirmed within days. The flyby represents the last experimental test before the comet fades beyond detection, and every possible outcome will rewrite how scientists understand interstellar visitors. Each theory will stand or collapse based on what Jupiter reveals when Atlas passes through its gravitational reach. This brings the chapter to its final question. Jupiter will reveal which theory survives and which ones collapse, but what will the sky show when the moment finally arrives? Atlas is fading by 1/10 of a magnitude every week, and soon its light will drop below the limits of almost every telescope on Earth. Only the Vera Rubin Observatory can still follow its path, yet even that instrument will lose sight of it by June as the object slips back into the dark. Scientists know this comet carries chemistry shaped inside a stellar system that died billions of years ago, and every observation may be the last chance to study material older than the Sun. The next 4 months are the final window to uncover answers before the mystery becomes unreachable forever. What happens during the Jupiter flyby will decide which theory stands, and once Atlas disappears, no new data will ever come again. So now the question passes to you. What do you think caused the tail to vanish? Fragmentation, depletion, or catastrophic crust formation?